In this video, we begin our proof of the Rogers-Ramanujan identities. So our intention is to go through the proof by Andrews and Baxter. It's called a motivated proof of the Rogers-Ramanujan identities. I'll provide a reference in the description below. But just as a reminder, the Rogers-Ramanujan identities say if n is a natural number, that the number of partitions of n into parts which are congruent to 1 or 4 mod 5 is equal to the number of partitions of n into parts which differ by 2 or more. So this is the first of the Rogers-Ramanujan identities. The second has similar conditions. It says the number of partitions of n into parts congruent to 2 or 3 mod 5 is equal to the number of partitions of n into parts greater than or equal to 2 which differ by 2 or more. And down below I've provided generating function expressions for each of these identities. So the congruence mod 5 conditions are represented by these infinite products, and the difference 2 conditions, as we saw in the first video, are represented by these infinite sums on the right-hand side of each equation. Okay, so one thing I'll point out is that it's very clear from the sum sides of the equations, so namely from the second half of these identities, that there are more of the first kind of partition, the kind of partition that appears in identity 1, than there are in identity 2, right? The reason is that the kind that appear on the right-hand side of identity 2 are the same that appear on the right-hand side of identity 1. We're just imposing an additional condition. We're restricting all parts to be bigger than or equal to 2. So in the second identity, we're not allowed to use 1s. In the first identity, we are allowed to use 1s as parts. So it's very natural to see from the sum sides that there are more of the first type of partition than of the second type of partition. This leads us to the question, this was a question originally posed by Leon Ehrenpreis, can this be seen from the product sides? So if I have these congruence mod 5 conditions, can I see that there are more partitions where parts are congruent to 1 or 4 mod 5 than there are partitions of n where parts are congruent to 2 or 3 mod 5? All right, so this was a question of Leon Ehrenpreis. So we will write this down here. This is Ehrenpreis's question. So can this be seen without knowledge of the Rogers-Ramanujan identities? So can we see that there are more partitions of n with parts that are congruent to 1 or 4 mod 5 than partitions of n with parts congruent to 2 or 3 mod 5 without resorting to using the Rogers-Ramanujan identities. So another way to reformulate this question is to say, okay, let G1 be the product side of the first Rogers-Ramanujan identity. So 1 minus q to the 5n plus 1 times 1 minus q to the 5n plus 4 as n, where n is bigger than or equal to 0, and G2 be the other product side, or the product side from the other Rogers-Ramanujan identity. So this is 1 minus q to the 5n plus 2, 1 minus q to the 5n plus 3, where n is bigger than or equal to 0. And so the idea is, can we show that G1 minus G2 has all non-negative integer coefficients? Non-negative integer coefficients without using the Rogers-Ramanujan identities. Right, so this is kind of the main motivation. So when we say motivated proof, this is kind of the question that motivates the proof. So the idea is going to be starting with just these product sides, can we prove this? And what's interesting about this is we're going to be led to a proof of the Rogers-Ramanujan identities by answering this question. Okay, so let's begin. So Andrews and Baxter in their paper, they first give some empirical observations. So what they do is they use a computer and they expand G1 and they expand G2. So they take the first 20 or so terms of each of these guys and they write them out. So for example, we can see that G1, if we use a computer to expand it out, it looks something like this: 1 plus q squared plus q cubed plus 2q to the 4th plus 2q to the 5th plus 3q to the 6th plus 3q to the 7th plus 4q to the 8th, so on and so forth, right? And again, what are these coefficients counting? The coefficient of q to the n is telling me how many partitions of n there are whose parts are congruent to 1 or 4 mod 5, right? So for example, the coefficient of q to the 4th is 2, because how do we partition 4 into parts that are congruent to 1 or 4 mod 5? Well, we could do 4 is equal to 4, that's one partition, or we could do 4 is equal to 1 plus 1 plus 1 plus 1. So those are our two partitions. Similarly, G2 counts the number of partitions of n where the parts we're allowed to use are 2 or 3 mod 5. So 1 plus q squared plus q cubed plus q to the 4th plus q to the 5th plus 2q to the 6th plus 2q to the 7th plus 3q to the 8th, plus so on and so forth. So we can use a computer to expand these out, and if we have a powerful enough computer, we can get as many terms as we'd like. But the empirical observation to make here is that if we subtract G1 and G2, we end up with a series of the following form. It's q times 1 plus q cubed plus q to the 4th plus q to the 5th plus q to the 6th plus q to the 7th plus 2q to the 8th, so on and so forth. And so what we can do is we notice that G1 minus G2 has a factor of q that we can pull out, and the remaining series, the series that appears in the parentheses, we're going to name it. We're going to define this series called G3. So I'm going to say define G3 to be G1 minus G2 over q, right? So G3 is precisely the series that appears in our parentheses. So this is the guy I'm going to name G3. It's precisely this series. Okay, so one thing to notice about G3 is it starts as 1 plus q cubed, so on and so forth. Right, starts as 1 plus q cubed plus, other terms. So at this point, we don't have a proof, right? Experimental evidence is not a proof in mathematics. So we're going to have to prove that all these coefficients are non-negative integers, right? We want to show that G3, all of its coefficients are non-negative integers. So we have our work cut out for us here. But we can do a little bit of further exploration. We could say, okay, now that we have this series G3, and again, with a powerful enough computer, we can write out as many terms as we like. But now that we have this series G3, what happens when we do G2 minus G3? Right? Mathematicians like to play with things like this. So we'll say, what happens when we do G2 minus G3? And miraculously, what we end up getting is a series of the form q squared times 1 plus q to the 4 plus q to the 5 plus q to the 6, plus q to the 7, plus q to the 8th, plus q to the 9th, plus 2q to the 10, and so on and so forth. It's an infinite series. This goes on infinitely. But the thing to notice is that in G2 minus G3, I can pull out this factor of q squared, right? So what I'm going to do is I'm going to define the following. I'm going to define G4 to be G2 minus G3 divided by q squared, right? So G4, just like before, G4 is going to be the thing that occurs in parentheses right here. Okay, and the thing to notice is, well, this series G4 starts as 1 plus q to the 4th plus higher power terms, right? So we're starting to notice some patterns here. We notice that the coefficients are all positive integers, or rather non-negative integers. We notice that G3 starts as 1 plus q cubed, G4 starts as 1 plus q to the 4th. If we look above, we can see that G2 starts as 1 plus q squared, G1 starts as 1 plus q to the 1. So we might start picking up on some patterns. And we might say, okay, well, what if I do G3 minus G4, right? Maybe this pattern breaks down. So we can compute G3 minus G4 and say, okay, well, if I do G3 minus G4, I plug this into my computer, and I'll see that G3 minus G4 is something of the form q cubed times 1 plus q to the 5th plus q to the 6th plus q to the 7th plus q to the 8th, so on and so forth. Right? This goes on infinitely. And what I'm going to do is, similar to above, I'm going to define G5 to be G3 minus G4 over q cubed. Right? And the thing that I might notice is this starts as 1 plus q to the 5th plus higher power terms. So we're kind of onto something, right? We're kind of onto something. We have a general pattern for how we can define these expressions. And so we can come up with a general definition. So in general, taking our G1 and G2 as above, we are going to define the series Gi, so define for I greater than or equal to 3, the series G sub I. This is going to be G sub I minus 2 minus G sub I minus 1 divided by Q to the I minus 2. So this is just following the pattern that we're observing above. And we're going to write down what's called the empirical hypothesis in the work of Andrews and Baxter. So what does the empirical hypothesis say? So our goal for this video is to prove the empirical hypothesis and to hopefully eventually answer Aaron Price's question. So we'll probably do that in the next video. But what is the empirical hypothesis? The empirical hypothesis is that the polynomial G sub I, or rather the series G sub I, can be expressed as 1 plus the sum of AIN, Q to the n, where n goes from I to infinity. So basically, we want to show that the series starts as 1 plus a whole bunch of zeros plus a q to the I term, a q to the I plus 1 term, so on and so forth, right? Just like we noticed G5 starts as 1 plus q to the 5th, so on and so forth. So basically, we want to show that this is an element of the set 1 plus q to the I times power series in Q. So this is kind of our goal for our video today. Okay, so to attain our goal, we have to do some clever rewriting of G1 and G2. So right now we're stuck with this expression where G1 is an infinite product and G2 is an infinite product. So it'd be great if we could somehow express these as infinite sums and sums that don't require the Rogers-Ramanujan identities. So we're going to be a little bit clever about this. So here's what we're going to do. We're going to take our expression G sub 1. Right? We might remember G sub 1 is the product of 1 over 1 minus q to the 5n plus 1 times 1 minus q to the 5n plus 4, as n goes from 0 to infinity, or n is bigger than or equal to 0. What we're going to do is we're going to rewrite this as the product where n is greater than or equal to 0. So I'm going to multiply the numerator and denominator by 1 minus q to the 5n plus 2, 1 minus q to the 5n plus 3, and 1 minus q to the 5n plus 5. So we're going to get an expression that looks something like this: 1 minus q to the 5n plus 1, 1 minus q to the 5n plus 2, so on and so forth, right? So all of these terms get expressed down here. Okay, so we end up with a product that looks like this. And we might notice that there's, if we cancel, we get back to the product we started above, right? If I cancel this term with this term, we get back to where we started above. If I cancel this term with this term and this term with this term, right? The thing to observe here, however, is that in this denominator, every single natural number, rather positive natural number, is represented as a power of q, right? So so one thing to notice here is that if you have any natural number, it can be represented as either 5n plus 1, 5n plus 2, 5n plus 3, 5n plus 4, 5n plus 5 for some n bigger than or equal to 0. So we can rewrite this in an even more clever way. We can write this as n greater than or equal to 0. And at the top, I'll write 1 minus q to the 5n plus 5. I'll just reorder things a little bit. 5n plus 2, 1 minus q to the 5n plus 3. And then at the bottom, we've represented every single positive natural number, so I'll write q sub infinity down here. Okay, so maybe I'll move this product up so it's kind of not ambiguous where the product sits. So this is the product where n is bigger than or equal to 0, and the product that occurs in the numerator. One thing I'll point out is we can do something similar. So similarly, we can write G2 as the product as n is greater than or equal to 0 of 1 minus q to the 5n plus 5, 1 minus q to the 5n plus 1, and 1 minus q to the 5n plus 4, divided by q sub infinity. And to just to recall, this q sub infinity is our Pockhammer symbol. So just to kind of recall what this is, this q sub infinity is just the product 1 minus q to the k as k goes from 1 to infinity. All right, this is our Q-Packheimer symbol. Okay, so how am I going to rewrite these infinite product expressions as sum expressions? Well, we saw in the last video that there was this thing we proved called the Jacobi triple product identity. Namely, it was an identity that identified an infinite sum with an infinite product. So we're going to use the Jacobi triple product identity, but we're going to use one of the alternate forms of the Jacobi triple product identity that we found. Right? So we're going to do the following. So we're going to rewrite G1, and I'll leave G2 as an exercise. Right, so we're going to rewrite G1, this infinite product expression, as an infinite sum. So the one thing to recall here is the Jacobi triple product identity. So recall the Jacobi triple product identity. Okay, so the form that we're going to recall is going to be the following form. We have that 1 plus the sum, m goes from 1 to infinity, of negative 1 to the m, q to the m squared, z to the minus m, times 1 plus z to the 2m. This is equal to the infinite product of 1 minus q to the 2n plus 2, 1 minus z q to the 2n plus 1, 1 minus z inverse q to the 2n plus 1, as n goes from 0 to infinity. So this was our infinite product. And what we're going to do in this Jacobi triple product identity is we're going to make a very clever substitution. So we're going to make the following substitution. So I'm going to replace q with q to the 5/2. And I'm going to replace z with q to the 1/2. Okay, so let's make this substitution in our expression, right? So the left-hand side is going to become 1 plus the sum negative 1 to the m. M goes from 1 to infinity. Here we're going to end up with a q to the 5/2 m squared. Z gets replaced by q to the 1/2, so I'm going to have a q to the minus m over 2. And in the parentheses here, again, z gets replaced by q to the 1/2, so q to the 1/2 to the 2m ends up just being q to the m. All right, so on this side, we end up with an expression that looks like this. All right, so I've made my substitution. On the product side, I'm going to end up with an expression that looks like this. I'm going to take the product as n goes from 0 to infinity. Again, q is being replaced by q to the 5/2, so q to the 5/2 to the 2n plus 2 becomes 1 minus q to the 5n plus 5. Our expression right here becomes 1 minus q to the 1/2 q to the 5n plus 5/2. And finally, our last expression becomes 1 minus q to the minus 1/2 q to the 5n plus 5/2. Right, so we can simplify this product quite a bit. What I'm going to do is I'm going to rewrite it in the following way. I'm going to say this is the sum, 1 plus the sum, m goes from 1 to infinity, of negative 1 to the m, and we'll write this exponent of q as 5 times m choose 2 plus 2m times 1 plus q to the m. And the product side is rather elegant. The product side is going to look very familiar in a second. So this is the sum, the product n goes from 0 to infinity of 1 minus q to the 5n plus 5, 1 minus q to the 5n plus 3, 1 minus q to the 5n plus 2. So we get a product side that looks like this. Now, why did I use this funny notation? Why did I use this 5 times m choose 2 plus 2m? Well, one of the reasons I use this is simply because it occurs in the Andrews and Baxter paper. But let's kind of explain this notation here, right? So what is this notation? So I'm using the fact that m choose 2 is simply m times m minus 1 over 2, right? So it's our standard binomial coefficient. So that when I write 5 times m choose 2 plus 2m, what I'm really just looking at here is 5 times m squared minus m over 2 plus 2m. And if I simplify this expression, I see that this is just 5m squared over 2 minus m over 2. All right, so this is what I'm looking at here. I'm looking at this type of expression. So really all I'm doing is I'm taking q to the 5/2 m squared times q to the minus m over 2 and just rewriting it in this nice way. So this is going to be our first necessary expression, right? So I'm going to look at this expression that I've written here, and I'm going to use it to rewrite my G1 as an infinite sum. So let's do that right now. So what I'm going to do is I'm going to rewrite G1, which again, if you recall, this was the product 1 minus q to the 5n plus 5, 1 minus q to the 5n plus 3, 1 minus q to the 5n plus 2, as n goes from 0 to infinity, over q sub infinity. I can now rewrite this infinite product as the sum 1 plus sum negative 1 to the m, q to the 5 times m choose 2 plus 2m times 1 plus q to the m, as m goes from 1 to infinity, and we'll leave the denominator unchanged. So now I have this expression for G1, and if I want to start looking at G1 minus G2, this allows me to do that a lot more nicely, right? Subtracting two infinite sums is a lot easier than subtracting two infinite products typically. So a similar substitution can be used in G2, and I'll leave this as an exercise. So here's an exercise to try. So substituting, I'm going to replace q with q to the 5 halves and z with q to the 3 halves afterwards into the Jacobi triple product identity, will leave me with the following expression for G2. So we use the same form of the Jacobi triple product identity. It's going to leave us with the following expression for G2. G2 is going to be 1 plus the infinite sum as m goes from 1 to infinity of negative 1 to the m, q to the 5 times m choose 2 plus m times 1 plus q to the 3m. 1 plus q to the 3m divided by q sub infinity. So this will be left as an exercise. Alternatively, we have another form of the Jacobi triple product identity that we talked about last time. So alternately, and again, this will also be a nice exercise. If we use the Jacobi triple product identity sum m greater than or equal to 0 of negative 1 to the m, q to the m squared, z to the m, times 1 minus q to the 2m plus 1, z to the minus 2m minus 1 is equal to our triple product. So is equal to the product of 1 minus q to the, again, 2n plus 2, 1 minus zq to the 2n plus 1, and then 1 minus z inverse q to the 2n plus 1, as n goes from 0 to infinity. If we use this expression and make the same substitution, we get another form for G2. We get that G2 can be rewritten as the sum, m going from 0 to infinity, of negative 1 to the m, q to the 5 times m choose 2 plus 4m times 1 plus q to the 2m plus 1 divided by q sub infinity. So I'll leave these two as exercises because these are actually good practice substituting into the Jacobi triple product identity. So this is a very commonly used identity to rewrite infinite products as infinite sums. So now we're finally ready to compute G3, right? And based on our computation from G3, we might be able to make a conjecture for what the general GIs look like. So what I'm going to do is I'm going to take the G1 sum expression I wrote down earlier, and I'm going to take this G2 sum expression right here and use it to compute an expression for G3. So let's do that. Okay, so let's write out our expressions. Let's see what we have. We have G3, well, this guy is G1 minus G2 over Q. Okay, so what does this look like when I expand this out? Well, both of my sums for G1 and G2, they start with 1 plus, right? So the first term is 1. So if I subtract the two series, I'll notice that the 1 plus terms cancel out. I have 1 plus a series minus 1 plus another series, so the 1's cancel. And I could write down these rather nice expressions. I could write this as the sum as m goes from 1 to infinity of negative 1 to the m, q to the 5 times m choose 2 plus 2m times 1 plus q to the m. So this is my expression for g1 from earlier, and minus the sum m goes from 1 to infinity of negative 1 to the m, q to the 5 times m choose 2 plus m times 1 plus q to the 3m. And now what am I dividing by? Well, they both had a q sub infinity in the denominator, but they also have a q in the denominator, right? Because we're dividing by this q right here, so I'll include it down there. Okay, so let's try to simplify this just a little bit. The first thing I'm going to do is I'm going to pull off one of the q to the m terms and distribute it into this factor right here. So the first thing I'm going to do is pull out one of the q to the m terms. So I'm going to write this as the sum of negative 1 to the m, q to the 5 times m choose 2 plus m times q to the m plus q to the 2m. And then I'm going to leave the other term alone. So this is still just negative 1 to the m, q to the 5 times m choose 2 plus m times 1 plus q to the 3m. M goes from 1 to infinity in both of my sums. So m goes from 1 to infinity, m goes from 1 to infinity, and I divide by q sub infinity. Okay, so now what I'd like to do is I'd like to notice that they have, I can write this as one expression. They in some sense have common factors I can pull out. So I'm going to rewrite this as one expression. So this is going to be the sum, m goes from 1 to infinity, of negative 1 to the m, q to the 5 times m choose 2 plus m. And now in parentheses here, I can write q to the m plus q to the 2m minus 1 minus q to the 3m. And this is all divided by q times q sub infinity. So we get this rather nice expression. Okay, so now our series starts at 1 and goes up to infinity. What I'm going to do is I'm going to re-index it. So I'd like my series to start from 0 and go up to infinity. So now I'm going to re-index my series. I'm going to re-index, and I'm going to swap my m's with m plus 1's. So that means my series now has to start at m equals 0 to infinity. All right, so what is my series going to look like? This is going to now equal the sum of negative 1 to the m plus 1, q to the 5 times m plus 1 choose 2 plus m plus 1 times q to the m plus 1 plus q to the 2m plus 2 minus 1 minus q to the 3m plus 3 divided by, well, now m is going to go from 0 to infinity, divided by q times q sub infinity. Okay, so let's interpret some of our expressions here. One of the things that I might notice right away is that the q in the denominator is going to cancel with the extra q that I have up here. So I can eliminate this q right away. Another thing I can do is I notice that I have this negative 1 to the m plus 1, so I could pull off a factor of negative 1 and distribute it into this product right here. So I'm going to do precisely that. So I'm going to rewrite this now as the sum m goes from 0 to infinity of negative 1 to the m, q to the 5 times m plus 1 choose 2 plus m. And I'm going to distribute that extra negative 1 in. So I'm going to have something that looks like 1 plus q to the 3m plus 3 minus q to the m plus 1 minus q to the 2m plus 2. All right, and then my denominator is just q sub infinity. All right, my denominator is this because the q canceled above. Okay. The other thing I might ask is, well, what can I do with this m plus 1 choose 2? So this expression simplifies rather nicely. So let's kind of simplify some of these expressions a little bit further, right? So the one thing to notice, so maybe I'll write this in a different color, right? The one thing to note is the following. If I look at m plus 1 choose 2, this is going to be m plus 1 times m divided by 2, right? So this expression is just m squared plus m over 2, which I can rewrite as m squared minus m over 2 plus m. So this expression here is just m choose 2 plus m. So that's the first observation I'm going to make. The second observation I'm going to make is that this term that occurs in the parentheses right here can be rewritten. It can be factored. So the first thing I'm going to notice is if I look at this expression, maybe we'll choose a different color for this expression, choose green, we can write 1 plus q to the 3m plus 3 minus q to the m plus 1 minus q to the 2m plus 2 as 1 minus q to the m plus 1 times 1 minus q to the 2m plus 2. We can factor this out this way. Okay, so that's exactly what I'm going to do in my series above. So now I can continue with my series. I could write this as the sum, m goes from 0 to infinity, of negative 1 to the m, q to the, well, let's see, 5 times m plus 1 choose 2 is going to become 5 times m choose 2 plus 5m plus the extra m that we have there, so plus 6m. And the term in parentheses factors as 1 minus q to the 2m plus 2, 1 minus q to the m plus 1. And again, this is all divided by q sub infinity, right? So we have an expression of this form. And at this point, you might notice that one of the terms here can be rewritten in terms of our Q-Packheimer notation. Namely, if I look at this term right here, I can rewrite this as q to the m plus 1 semicolon q sub 1. Okay, so let's rewrite our series in terms of the Q-Packheimer symbol. So this is going to be the sum, m goes from 0 to infinity, of negative 1 to the m, q to the 5 times m choose 2 plus 6m, times q to the m plus 1, q sub 1, times 1 minus q to the 2m plus 2, all divided by q sub infinity. Okay, so we have our expression for G3, right? Recall, this is our G3. And using our second version of the Jacobi triple product identity, or a second rewrite of the Jacobi triple product identity, I have a similar expression for G2, right? So one of the things you might notice, the thing to recall here, so this is our G3, right? This guy right here, this is our G3. One of the things to recall is that we had an expression for G2 that looked like the following. So this is the sum, negative 1 to the m, q to the 5 times m choose 2 plus 4m, times 1 plus q to the 2m plus 1. And if we want, we could write q to the m plus 1 semicolon q sub 0. All right, so that term is just 1. This is the sum, m goes from 0 to infinity over q sub infinity. Okay, so we have these expressions for G1, and we have this, or rather for G3, and we have this expression for G2. And you might notice some similarities here between these two expressions, and you might be led to a conjecture. So let's write down a conjecture for G sub I, and then we'll work on proving this conjecture. All right, so this is a bit long-winded. So let's write down our conjecture for G sub I based on our G sub 3 and our G sub 2 that we have here. So here's our conjecture. So the conjecture is going to say, for I greater than or equal to 2, we have that G sub I can be written as the sum, negative 1 to the m, q to the 5 times m choose 2, plus, well, if I was equal to 2, we had a 4m. If I was equal to 3, we had a 6m. So I could write a 2im up here. We can write q to the m plus 1 semicolon q sub I minus 2 times 1 minus q to the 2m plus I minus 1 as m goes from 0 to infinity. And we're going to divide this by q sub infinity. So this is the conjecture that we're going to work to prove. So this expression that we have here, we're going to call it the first form of G sub I. So this expression right here is going to be the first, we'll call it the first form of G sub I. So this is not a name that's given in the paper. This is just a name that I'll use here. So when I refer to the first form of G sub I mean G sub I as it is written in the conjecture. One thing we're going to need is we're going to need a certain rewrite of our G sub I. So let's rewrite this conjectured sum. So I'd like to take the sum and we can rewrite it. So we can rewrite this sum. So let's be a little bit clever about how we rewrite this. So the first thing I'm going to do is I'm going to take my sum. M goes from 0 to infinity, -1 to the m, q to the 5 times m choose 2 plus 2im times q to the m plus 1 semicolon q sub I minus 2. And the 1 minus q to the 2m plus I minus 1, I'm going to rewrite it in the following way. I'm going to write this as 1 minus q to the m plus q to the m minus q to the 2m plus I minus 1. Right? So all I've done is I've basically just added 0 to the middle right here. Right? I've just added 0 there. Okay. What I'm going to do next is I'm going to, well, I forgot the q sub infinity. You can't forget the denominator. What I'm going to do next is I'm going to distribute. So I'm going to take the sum and multiply it by, or the factors on the left and multiply them by 1 minus q to the m. And then I'm going to take the factors on the left and multiply them by the leftover stuff right here. So let's do that expansion. So this expression can be written as the sum -1 to the m, q to the 5 times m choose 2 plus 2im, q to the m plus 1 semicolon q sub I minus 2 times 1 minus q to the m. M goes from 0 to infinity over q sub infinity. And the second expression, I can now rewrite this as the sum m goes from 0 to infinity of -1 to the m, q to the 5 times m choose 2 plus 2im, q to the m plus 1 semicolon q sub I minus 2, and times q to the m minus q to the 2m plus I minus 1. All right, so I could rewrite this expression this way. And again, of course, this is over q sub infinity. Okay, so we have a few things that we can notice here. One thing I can notice is that when m is equal to 0, this first expression becomes 1 minus q to the 0. So this is equal to 0 when m is equal to 0. So one thing I could do is instead, I can start my sum and have it go from 1 to infinity. Right? Another thing I can do is I can pull out a common factor of q to the m and just put it over here. All right, so I could pull out a common factor of q to the m and put it over here. So let's do that. Right, so the first sum stays the same. The sum m goes from 1 to infinity, -1 to the m, q to the 5 times m choose 2 plus 2im, q to the m plus 1, semicolon q sub I minus 1, 1 minus q to the m. The second term, what I'm going to do is I'm just going to factor out one of the q to the m. So this becomes -1 to the m, q to the 5 times m choose 2 plus 2im plus m times q to the m plus 1 semicolon q sub I minus 2 times 1 minus q to the m plus I minus 1. Right? And this sum as m goes from 1 to infinity. And I'm going to, again, divide both of these by q sub infinity. So this guy gets divided by q sub infinity. Okay, so we have an expression that looks like this now. Another thing that I can notice is that this 1 minus q to the m can be absorbed into this term right here. So if I expand out the q Pochhammer symbol, I might notice that 1 minus q to the m can be added to the beginning of the product that's given by this q Pochhammer symbol. So I'm going to do that. The other thing I might notice is that this term right here can also be added into this q Pochhammer symbol. Namely, it can be added as the last term. So if I were to expand out this q Pochhammer symbol, this product would occur as the last term. So let's do that rewriting. So I'm going to write this now as the sum of -1 to the m, q to the 5 times m choose 2 plus 2im times q to the m semicolon q sub I minus 1, where m goes from 1 to infinity, divided by q sub infinity, plus the sum, m goes from 0 to infinity, and just a small correction, we should have m equal to 0 in the first series. So the sum m goes from 0 to infinity of -1 to the m, q to the 5 times m choose 2 plus 2im plus m times q to the m plus 1 semicolon q sub I minus 1 divided by q sub infinity, right? So we have an expression that looks something like this now. Where do we go from here? Well, the first thing I might notice is I want to combine these two series somehow, but the first series starts at m equals to 1. The second series starts at m equals to 0. So there's a little bit of a complication there, not too much. But what I'm going to do is I'm going to use the same trick as before, and I'm going to reindex the first series. So I'm going to replace all of my m's by m plus 1s and start the series at 0. All right, so I'm going to do that. So let's reindex this series. I'm going to write this as the sum, m goes from 0 to infinity, of -1 to the m plus 1, q to the 5 times m plus 1 choose 2, plus 2i times m plus 1, times q to the m plus 1, semicolon q sub I minus 1, all over q sub infinity, plus the sum of -1 to the m, q to the 5 times m choose 2, plus 2im plus m, q to the m plus 1, semicolon q sub I minus 1, as m goes from 0 to infinity, divided by q sub infinity. Okay, so we've rewritten our expression. We've reindexed the first term, or the first sum, rather. And now we're going to do the same trick as earlier. I recall that this m plus 1 choose 2 can be rewritten, right? So namely, the thing I want to recall that 5 times m plus 1 choose 2 can be written as 5 times m choose 2 plus 5m, right? So we used this a little bit earlier, and so I'm going to do precisely that rewriting, right? I'm going to do precisely that rewriting. So I'm going to say, okay, this is now the sum. So I'll pull out a -1 also, right? So I have a -1 to the m plus 1 up here. I'm going to take a -1 to the 1 and kind of pull it out and write a negative in front. So this is going to be the sum. M goes from 0 to infinity. And let's see what this looks like. This is going to be -1 to the m, q to the 5 times m choose 2, plus 5m plus 2im plus 2i times q to the m plus 1 semicolon q sub I minus 1 over q sub infinity, plus the same sum as before. So this is -1 to the m, q to the 5 times m choose 2, plus 2im plus m times q to the m plus 1 semicolon q sub I minus 1, m goes from 0 to infinity, over q sub infinity. Okay, so now our hard work is almost done, because now what I can do is I can combine these two series, right? I can combine these two series. So I can collect like terms and rewrite this as the sum -1 to the m, q to the 5 times m choose 2, plus 2i plus 1 m times q to the m plus 1 semicolon q sub I minus 1 times 1 minus q to the 4m plus 2i, as m goes from 0 to infinity, divided by q sub infinity, right? So this is what we end up with, and we're going to refer to this as the second form of g sub I, of our series g sub I. So this guy is going to be referred to as our second form. So it's our alternate way of rewriting that infinite sum that we're conjecturing to be our g sub I, right? So I'm going to call this the second form. So now we're finally ready to prove our formula for g sub I, right? So we've already proved that the middle term is equal to the right-hand term, and the first form is equal to the second form. The thing that's left to show is that these both actually equal g sub I. So here's what I'm going to do. I'm going to look at my expression for g sub I. So my expression for g sub I is g sub I minus 2 minus g sub I minus 1 divided by q to the I minus 2. And what I'm going to do is I'm going to use the second form of g sub I minus 2, and I'm going to use the first form of g sub I minus 1. So I'm assuming, so I already proved my claim for g sub 2 and g sub 3. I'm going to assume that we're going to induct on I. I'm going to assume that it holds for g sub I minus 1 and g sub I minus 2. And for g sub I minus 2, I'll use the second form. For g sub I minus for g sub I minus 2, I'll use the second form. For g sub I minus 1, I'll use the first form. So let's do this rewriting. So what does this look like? This is 1 over q to the I minus 2, q sub infinity. And if I plug in my two forms, what do I get? I'm going to get that this is the sum of negative 1 to the m, q to the 5 times m choose 2, plus 2i minus 3 times m, times q to the m plus 1, semicolon q, sub I minus 3, times 1 minus q to the 4m plus 2i minus 4. Okay, so that's my first sum. Right, m is bigger than or equal to 0. What I'm going to do is I'm going to now subtract g sub I minus 1. I'm going to use the first form of my expression. So this is going to be negative 1 to the m, q to the 5 times m choose 2, plus 2i minus 2 times m, q to the m plus 1, semicolon q, sub I minus 3, times 1 minus q to the 2m plus I minus 2. And m is going to go from 0 to infinity again. So I have an expression that looks like this. And what I'm going to do is I'm going to collect all the common terms in my expression, right? So I'm going to combine these all into one sum. I'm going to collect all the common terms. So the way that this is going to get rewritten when I collect all the common terms is 1 over q to the I minus 2, q sub infinity. And let's see what I can pull out from everything. I could write this as the sum, m greater than or equal to 0. Well, they all have a negative 1 to the m in common. They all have a q to the 5 times m choose 2 in common. And they all have a 2i minus 3m in common in the power of q. So 2i minus 3 times m. And they all have a q to the m plus 1 semicolon q sub I minus 3. So this is going to be q to the m plus 1 semicolon q sub I minus 3. Now, what do they have that's not in common? Well, there's this term that's not in common, and there's a q to the m and this term that are not in common. So I can now just rewrite this as 1 minus q to the 4m plus 2i minus 4 minus q to the m times 1 minus q to the 2m plus I minus 2. And the one thing I'm going to do is I'm going to cleverly rewrite this term in parentheses. So I'm going to take this term in parentheses and do a clever rewrite of this. Namely, I'm going to write this as 1 minus q to the m plus q to the 3m plus I minus 2 times 1 minus q to the m plus I minus 2. So I'll let you check that this actually agrees with the expression above. Okay, so what I'm going to now do is I'm going to distribute. So I'm going to take this expression and multiply it by 1 minus q to the m. And then I'm going to take this expression and multiply it by this whole term right here. All right, so I'm going to take these expressions and multiply them out. So we're going to get a big long expression, but this big long expression is going to simplify rather elegantly. All right, so I'll write this as 1 over q to the I minus 2 q sub infinity times the sum of negative 1 to the m, q to the 5 times m choose 2 plus 2i minus 3 m times q to the m plus 1 semicolon q I minus 3 times 1 minus q to the m. All right, so that's my first term, or my first sum. M goes from 0 to infinity. And the next sum, again, recall I'm going to take this series right here, or this part of the series right here, and multiply it against the latter two terms. So what is this going to give me? This is going to be the sum. M goes from 0 to infinity, so m greater than or equal to 0, of negative 1 to the m, q to the 5 times m choose 2, plus 2I minus 3 times m. And there's this extra q to the 3m plus I minus 2, so I'm going to write this up here. I'm going to write this as plus 3m plus I minus 2. And then I have my q to the m plus 1, semicolon q sub I minus 3, and then a 1 minus q to the m plus I minus 2. So this big, long expression, right? So this big, long expression. Now, the nice thing that I can do is I can simplify this a little bit now, right? I can clean up this exponent right here. I can combine these into their own Q-Pochhammer symbol, and I can combine these into their own Q-Pochhammer symbol. So let's do all of that, right? Let's do all of that simplification. So I'm going to write this as 1 over q to the I minus 2, q sub infinity, times the sum. Oh, and the other thing I can notice is that when m is equal to 0, this term is 0. I get 1 minus q to the 0, so I get 1 minus 1. So I can start the sum like before, like in some of the other examples earlier, at 1 and go to infinity. So it's m goes from 1 to infinity of negative 1 to the m, q to the 5 times m choose 2, plus 2I minus 3m, times, when I combine 1 minus q to the m times the Q-Pochhammer symbol, it combines into q to the m semicolon q sub I minus 2. All right, so when I combine these two guys up here, they turn into this rather nice expression. I'm also going to now clean up the second sum a bit. So this is going to be the sum. M goes from 0 to infinity of negative 1 to the m, q to the 5 times m choose 2. And I'm going to clean up the mess that we have in the exponent. When I clean up the mess that we have in the exponent, this is going to be plus 2im plus I minus 2. And finally, what I'm going to do is I'm going to combine these into one Q-Pochhammer symbol. So when I do that, I'm going to get q to the m plus 1, semicolon q, sub I minus 2. All right, so this is a lot cleaner already. Just like before, we're going to now just leave the second series alone. And we're going to re-index this first one. So it's the same trick kind of over and over again, where we notice that there's a term that's 0. We start the sum at 1 instead of 0 because the m equals 0 term doesn't contribute anything anyway, and then we re-index, right? So now I'm going to re-index that second series into, so I'm going to get 1 over q to the I minus 2, q sub infinity. And again, I'm going to replace all the m's with m plus 1s. So now when I re-index this guy, what does this series become? Right, what does this series become when I re-index? This is going to become the sum of negative 1 to the m plus 1, q to the 5 times m plus 1 choose 2, plus 2I minus 3 times m plus 1 times q to the m plus 1, semicolon q, sub I minus 2, right? M goes from 1 to infinity. And the second sum, like I said, I can just leave this alone for the time being, right? So the second sum I'm just going to leave alone. So plus negative 1 to the m, q to the 5 times m choose 2, plus 2im plus I minus 2. And this is just q to the m plus 1, semicolon q, sub I minus 2. Right, as m goes from 0 to infinity. And again, since I re-index, this first sum should go from 0 to infinity as well. Okay, so let's clean this up a little bit. Recall that m plus 1 choose 2 is m choose 2 plus m, right? So I can rewrite this guy. I can now take this as 1 over q to the I minus 2, q sub infinity. And let's see what we have here. So I'm going to take a factor of negative 1 and pull it out. So I'll write this as negative the sum, m goes from 0 to infinity, of -1 to the m, q to the 5 times m choose 2 plus 5m. And let's simplify what else we have, right? We're going to have a plus 2im, a minus 3m, and then we're going to have a plus 2i minus 3. And this term stays the same. This is going to be q to the m plus 1 semicolon q sub I minus 2. And then plus the sum -1 to the m goes from 0 to infinity, q to the 5 times m choose 2, plus 2im plus I minus 2, q to the m plus 1, q sub I minus 2. So the second sum stays the same. Okay, now we might notice that there's some kind of clever rewriting we might be able to pull off here. So we can kind of simplify some of these expressions quite a bit. One thing we might notice right away is that this 5m and this -3m, they combine into 2m, right? So that's rather simple. The other thing I might notice is that this 2i minus 3 can be rewritten as I minus 1 plus I minus 2. Right, so there's an I minus 1 plus I minus 2 up here. And what this allows me to do is to pull out a factor of q to the I minus 2, right? So now what I can do is I can say, well, let's rewrite this. This is 1 over q to the I minus 2, q sub infinity, times negative the sum, m goes from 0 to infinity. Let's write out the cleaned up version. So q to the 5 times m choose 2, plus 2m plus 2im, and then we could write this as plus I minus 1 plus I minus 2 times q to the m plus 1 semicolon q sub I minus 2. And again, leave the second sum alone. So we're not going to do anything to the second sum. We're just going to, it's already rewritten how we want to write it. We'll see why in a second. So this is going to be q to the 5 times m choose 2 plus 2im plus I minus 2 q to the m plus 1 semicolon q sub I minus 2. Now, what do we notice right away? We notice that this q to the I minus 2 can be canceled, right? There's a q to the I minus 2 term I could pull out here, and there's a q to the 2i minus 2 term that I can pull out here. So I'm able to cancel these guys out. Once I've canceled these terms, I can notice another thing. I can notice that I can combine these all into one sum. So now I could write this as 1 over q sub infinity. Sum m goes from 0 to infinity. What terms do they have in common? There's a -1 to the m they have in common. There's a q to the 5 times m choose 2 that they have in common. There's a 2im that they have in common. There's a q to the m plus 1 semicolon q sub I minus 2 that they have in common. And what's left over? Well, I've used up all the terms from the first series, or from the second series, right? So I've used up basically all the terms here, but what's left over here? The thing that's left over here is a 2m and an I minus 1, right? So this is going to be minus q to the 2m plus I minus 1. So hence, GI is of the desired form. So GI is of the desired form. Okay, so we've proved that GI takes the form that we want it to take. Okay, so now we've finally shown that GI takes the form that we kind of conjectured that it would. So now we can finally begin our proof of the empirical hypothesis. And once we have this desired form for G sub I can prove the empirical hypothesis. So how do I prove this? Well, what I'm going to do is I'm going to separate off the m equal to 0 term from the rest of the terms. So I can write G sub I as, if I separate off the m equals 0 term, I'm going to have a -1 to the 0, a q to the 5 times 0 choose 2 plus 2i times 0. So what are the terms that are going to survive when I plug in m is equal to 0? I'm going to have q to the 0 plus 1, so q to the 1 semicolon q sub I minus 2. I'm going to have a 1 minus q to the 2 times 0 plus I minus 1 divided by q sub infinity. Right? So I have an expression that looks like this. Again, these terms right here, negative 1 to the 0 is just 1. And then these terms right here are just q to the 0. Right? So those are just going to be q to the 0. So q to the 0 is 1. So this is going to be the m is equal to 0 term. Right? So this is the m is equal to 0 term. What are the other terms? Well, the other terms are just the same exact sum that I have up here. Right? So the other terms are just 1 over q sub infinity times the sum, m goes from 1 to infinity, of negative 1 to the m, q to the 5 times m choose 2, plus 2im, times q to the m plus 1, semicolon q sub I minus 2, times 1 minus q to the 2m, plus I minus 1. All right, so this is what our expression looks like. So let's simplify the first term, the m is equal to 0 term. So if we expand this term out, we notice that, what does this look like? Well, the q Packheimer symbol, it's 1 minus q squared, all the way up to 1 minus q to the I minus 2. That's our q Packheimer symbol. We also have this 1 minus q to the I minus 1 up here. And this is all divided by, well, what's the denominator? The denominator is 1 minus q squared. This is going to continue until we get to 1 minus q to the I minus 1, 1 minus q to the I, so on and so forth. And it's just going to continue on infinitely, right? This just continues on infinitely. What else can I notice? I can notice that from the series that I have written here, I can pull out a q to the 2i. So I can now write this as q to the 2i, 1 over q sub infinity, times the sum, m goes from 1 to infinity, of negative 1 to the m, q to the 5 times m choose 2, plus 2im minus 2i, times all of the stuff that we had up here, right? So times all of this kind of stuff that we had up here, right? So times this. Okay. And notice that this expression still makes sense. When m is equal to 1, the power of q that occurs here is still a positive integer, right? So if I factor out this q to the 2i, this power of q is still going to be a positive integer. Okay, so let's cancel this out. Just let's cancel out some more terms, right? So we have 1 minus q cancels, 1 minus q squared cancels. Everything cancels up to 1 minus q to the I minus 1, right? So all of those guys cancel. And what am I left over with when I do that? I'm left with 1 minus q to the I, 1 minus q to the I plus 1, so on and so forth, plus q to the 2i times some power series. So this stuff that's in that power series, it doesn't matter what it is, but it's some power series where, so I'll say gamma sub I of q is just a power series in q. Right, gamma sub I of q is a power series in q, but notice that it's q to the 2i times this power series. So all of these terms here, they start as q to the 2i plus higher power terms. What about the series beneath it? Well, this guy right here, if I use my geometric expansion convention, the first 1 over 1 minus q to the I is 1 plus q to the I plus q to the 2i, so on and so forth. The second is 1 plus q to the I plus 1 plus q to the 2i plus 2, so on and so forth. And these continue, right? And I can look at the series and ask myself, well, what are the first few terms of this series? Well, if I multiply all the ones together, I'm going to get 1. What's the next power of q that occurs? Well, it's going to be q to the I times 1 times 1 times 1. So it's 1 plus q to the I, right? I should write this q to the 2i times gamma I of q up here as well. But what are the powers of q? They should be, well, the lowest power of q that occurs is q to the I times 1 times 1 times 1 times 1, right? The next lowest power of q that occurs is q to the I plus 1. So there's going to be a q to the I plus 1. How do I get that? Well, I do q to the I plus 1 times 1, and then all the other series subsequent will have 1s as well that I multiply by. So on and so forth, plus q to the 2i times gamma I of q. But what have I shown? When I look at this expression, this is going to be 1 plus q to the I plus higher powers of q. Right, plus higher powers of q. I don't really care what the powers are as long as they're larger than q to the I. So what have I shown? I've shown that gi is an element of 1 plus q to the I times power series in q. And thus I've proved my empirical hypothesis. Okay, in the next video, what we'll do is we'll finally prove the Rogers-Ramanujan identities, but in order to prove those identities, we needed to get to this empirical hypothesis first, right? So we'll prove the Rogers-Ramanujan identities. We'll give an answer to Ehrenpreis's question as well. So I'll stop here and we'll continue next time.